Hey everyone, welcome to this explainer. Today, we are zeroing in on mastering your Class 12 Physics Lab practicals. We're going to walk step by step through exactly how to verify the laws of series and parallel circuits using that classic piece of lab equipment, the meter bridge. And then we're going to flip the script entirely with a really fascinating look at capacitors. It's going to be a great session, so let's get right into it. Okay, let's dive into this. Think of this explainer as a chronological journey through a real lab session. We'll start with a quick refresher on series and parallel basics, get our hands dirty with the meter bridge setup, and test some resistor combinations. Then we hit a major plot twist with capacitors, test those out with multimeters, and finally wrap up with exactly what you need to know to ace your practical exam. All right, let's kick things off with Section 1, Series and Parallel Basics. Before we touch any actual lab equipment, let's just make sure we're completely aligned on the physical layout here. In a series circuit, components are connected end-to-end. It's literally a single, uninterrupted path for the current. But with a parallel circuit, your components are connected across common points. This gives the current multiple distinct branches or paths to travel through. Pretty straightforward, right? Now, the behavior of voltage and current in these setups is exactly reversed. In series, the current stays identically the same through every single component, but the voltage divides up. In parallel, it's the exact opposite. The current divides among those branches, but the voltage, that remains absolutely constant across all of them. And this brilliantly illustrates why our household appliances are wired in parallel. It ensures every single device gets that exact same voltage it needs to run properly. Moving right along to Section 2, the meter bridge setup. Now, what's really interesting about this slide is how we take a purely theoretical textbook concept and turn it into a physical device. The meter bridge is literally just a practical, real-world application of the Wheatstone bridge principle. Remember that? When the ratio of resistances in the two arms is completely equal. So P over Q equals R over S. No current flows through the middle. Zero. The bridge is perfectly balanced. So in the lab, we use a 1-meter wire and a sliding jockey connected to a galvanometer to physically hunt down that exact null point. But you might be wondering, why on earth don't we just use standard copper wire for that 1-meter stretch on the bridge? It's everywhere, right? Well, there's a catch. Copper has a high temperature coefficient of resistance. As current flows through it, the wire naturally heats up, and copper's resistance would change significantly, completely ruining the accuracy of our readings. No way we want that. Instead, we use specific alloys like constantan or manganin. They not only offer high resistance, but crucially, they have a very low temperature coefficient. That means the resistance stays rock solid, even as they warm up during your experiment. Okay, let's get our hands on the equipment. Section 3, Testing Resistor Combinations. So how do we actually find the value of an unknown resistance coil placed in our right gap? We use a specific mathematical formula derived directly from that Wheatstone principle we just talked about. It goes like this. Little r equals 100 minus L divided by L, and then you multiply that whole thing by big R. Now, big R is the known resistance that we actively pull from our resistance box over in a left gap. And little L, that is our balancing length in centimeters. You literally find L by gently sliding your jockey along the wire until your galvanometer needle rests perfectly dead center at 0. Let's move to a parallel and see how this builds in practice. To actually verify these laws, you can't just guess. You absolutely must methodically record your observations in this exact tabular format. It's like a giant puzzle. First, you test resistor 1 all by itself, hunt down your balancing length L, and calculate R1. You actually do this 3 times to get a solid mean resistance. Then you repeat the whole shebang for resistor 2. Finally, you connect R1 and R2 together, first setting them up in parallel and then in series to find your combined experimental resistances. And here's where it all comes together, the verification. You take those mean experimental values you just carefully calculated for your series and parallel combinations, and you stack them up against the theoretical textbook formulas. For a series circuit, the theoretical resistance is just R1 plus R2. Super simple. For parallel, it's R1 times R2 divided by R1 plus R2. If your hard-earned experimental values closely match these theoretical ones, boom, congratulations, you have successfully verified the laws of combination for resistors. But hold on, because here is where things get wild. Section 4, the capacitor plot twist. We've mastered resistors, right? But what exactly happens to our math if we just swap out those resistors for capacitors? Think about it. If you go back to your circuit, yank out the resistance coils, and plug in capacitors instead, do they behave the exact same way? Do those same trusty mathematical formulas still apply? So the crucial point is that they absolutely do not. It's a total plot twist. The mathematical laws for combining capacitors are a complete, literal mirror image of the laws for resistors. Remember how resistors in series simply add together like 1 plus 1? Well, for capacitors, it's the parallel connection that acts additively. Total capacitance in parallel is just C1 plus C2. And conversely, while resistors in parallel use that complicated reciprocal formula, capacitors actually require that reciprocal formula when connected in series. It is a complete 180-degree physical inversion of the math. How cool is that? All right, let's test this out. Section 5. Testing capacitors with multimeters. Now, testing capacitors isn't like testing resistors. It requires some very deliberate, careful physical steps, mostly so you don't accidentally fry your lab equipment. Step 1 is absolutely critical, guys. You must completely discharge the capacitor first by connecting it across a resistor. If you skip this, any stored charge is going to zap your multimeter. Once you're safely discharged, connect the capacitor's longer, positive lead to the red probe and the shorter, negative lead to the black probe. Finally, just twist your multimeter knob over to capacitance mode and wait for the magic reading. To put this into perspective, take a look at this real-world result from an actual student's physics investigatory project, 2.02. What they did was take two standard 1 microfarad capacitors, hooked them up in parallel, and measured the combination. Now, theoretically, based on our new additive law for capacitors in parallel, 1 plus 1 should equal exactly 2 microfarads, right? The multimeter actually read 2.02. That incredibly tight match beautifully and practically proves this inverse law in real life. It's so satisfying to see the math work out perfectly on the bench.
Okay, let's bring it all home. Section 6, Acing Your Practical Exam.
Listen up, because these are the vital precautions examiners are actively looking for. First, always clean your connecting wires with a bit of sandpaper to scrub off any insulating oxide layers. Second, physically rotate and tighten every single plug in your resistance box. Just one loose plug introduces hidden, unknown resistance that will completely wreck your data. Third, never rub the jockey hard against the bridge wire. Actually, scratch that. Don't rub it at all. Scraping it alters the wire's cross-sectional area, permanently changing its resistance per unit length. And finally, always remove the battery key when you aren't actively taking a reading. This prevents the circuit from heating up. Ignoring these simple rules will introduce massive errors and for sure cost you precious marks on the CBSE board exam.
So, as we wrap up this explainer, I really want to leave you with this one thought. We've just seen how series and parallel connections govern the flow of electricity, and how simply swapping a single component from a resistor to a capacitor turns the mathematical laws entirely upside down. It really makes you wonder, if simply swapping a resistor for a capacitor can completely invert the mathematical laws of a circuit, what other hidden mirror images and surprising physical relationships are just waiting to be discovered in your physics lab? Keep asking those questions, keep meticulously verifying those laws, and above all, keep learning. Thanks for joining me.